Hello viewers, myself Dr. T. Anoja here. I am going to present to you a new video on nuclear spin-spin couplings and splitting of NMR absorption peaks. This simple video will be very useful for beginners for understanding NMR spectra. So let us begin. For simplicity, we have divided the whole topic into several subtopics so that one can understand point-wise. These are the points which we'll be covering in this video. First, let us go with the introduction. A phenomenon that causes a splitting of some or all NMR absorption signals of a compound, giving fine structures, is described as a spin-spin coupling or J coupling or spin-spin splitting. These names are used. For example, the spectrum of acidified ethanol means ethanol added few drops of HCl in it. It produces a 1:2:1 triplet for the methyl hydrogens, a 1:3:3:1 quartet for the CH2 hydrogens, and a singlet for the hydroxyl hydrogen. However, when the spectrum of a super dry sample of ethanol is examined, the hydroxyl H absorbs as a triplet and the methylene hydrogens absorb as a multiplet, theoretically 8 unresolved lines, while the CH3 is still a triplet. This splitting arises as a result of indirect magnetic interaction between magnetically non-equivalent NMR active nuclei in the molecule. The interaction between the magnetic nuclei or magnetic dipoles is transmitted through the bonding electrons as they too are tiny bar magnets. Therefore, such couplings are called indirect coupling interactions between nearby spinning nuclei, which we often call tiny bar magnets. This kind of interaction changes the shape of NMR absorption, making them more complex, but in a predictable way. Obviously, the spectrum becomes complicated, but at the same time more informative. The magnitude of coupling depends upon several factors like element type, distance between the coupled nuclei, geometry, angle of inclination, that is the orientation of nuclear spins, but it does not depend on the strength of the magnetic field. That is the difference between chemical shift and J coupling. Chemical shift in terms of frequency depends on magnetic field, but J coupling is independent. It may be noted that chemical shift, when presented in the form of universal scale delta, then it does not depend on magnetic field, but when it is presented in the form of frequency, it does depend on magnetic field. Let us take one example here. 1,1-dibromo, 1,1-dichloroethane. The structure of the molecule is shown here. It contains chemically non-equivalent HA and HB. For differentiation, we have superscripted hydrogens. Theoretically, under very low resolution of NMR spectroscopy, two signals are obtained, one for HA, one for HB. But in normal case, the spectrum is recorded at high resolution, so both hydrogens appear as doublets. Two doublets appear in the spectrum. How to explain this? When hydrogen HA is absorbing, then the nucleus of HB has two possible orientations shown below with the dotted arrow. Likewise, when nucleus HB is absorbing, the nucleus HA has two possible orientations. That is why we get a doublet for each. Below the diagram, applied field direction is shown. It is increasing from left to right. Chemical shift direction is also shown. It is increasing from right to left. and chemical shift value in terms of delta for hydrogen Ha is greater than hydrogen Hb assumed. So I repeat these points. At low resolution spectrum, the broad peak for Ha at delta A and the broad peak for Hb at delta B. High resolution spectrum shows 1 doublet for Ha and also 1 doublet for Hb. The separation between the components of each doublet is called the splitting constant, symbol J, unit Hajar cycles per second. The splitting of peaks is mutual. This is very important point to note. The splitting of peaks is mutual and J value is field independent but depends on element type, distance, geometry or angle of orientation of the nuclei which are coupled together. Let us proceed with another example. Example 2, 1-bromo, 2,2-dichloroethane. Formula is shown here. Cl2CH CHHBr. This molecule contains chemically non-equivalent HA, one type, and HB prime, another type. Two types of hydrogens are there in this molecule. It shows 1:2:1 triplet for HA and 1:1 doublet for the two hydrogens HB and HB prime. Both are chemically equivalent. So in nutshell, we get two signals, a triplet and a doublet. Chemically equivalent HB and HB prime absorb at the same field and they do not split each other's signal. Signal for HA is split by two protons, HB and HB prime, both are equivalent, into a triplet, 1:2:1 triplet. Signal for both HB and HB prime is split into a doublet, 1:1 doublet by HA. Let us take yet another example, 2-butanone. We can see very clearly this molecule contains three types of hydrogens. CH3 near carbonyl group, CH2, and the distant CH3. Three types of hydrogens are there. Both methyls are non-equivalent. So it gives a singlet for CH3 nearby CHCO. The other CH3, which is attached to CH2, gives a triplet. Splitting is caused by CH2 hydrogens. And CH2 absorbs as a quartet. Splitting is caused by CH3 hydrogens. So in this case, one CH3 appears as a singlet simply because J coupling is caused up to 3 single bonds, not beyond. So this simple compound gives a singlet, a triplet, and a quartet. Rules for splitting of signals. Chemically and magnetically equivalent nuclei do not mutually couple. Coupling between nuclei H, H or F, F is called homonuclear coupling. When both nuclei are the same type, then it is called homonuclear coupling. Heteronuclear couplings involve dissimilar nuclei like hydrogen and fluorine, hydrogen and phosphorus, etc. Effective couplings are observed up to 3 single bonds. Where conjugated pi bonds intervene, long-range couplings are observed. But for geometrical regions, two hydrogens come closer. Even if their bond separation may be more than 3, then coupling may occur through space coupling, long-range couplings, and couplings beyond 9 bonds have been recorded through space couplings only. Number of lines, that is multiplicity. It is given by the formula 2n1 plus 1 multiplied by 2n2 plus 1. Here I refers to the spin and n refers to the number of nuclei of each type. Suppose If only hydrogen nuclei are involved, then I is half. If nitrogen 14 is involved, I is 1, and so on and so forth. So N refers to the number of splitting nuclei with spin I, particular spin I. Get another example, chloroethane, CH3, CH2, Cl. We are discussing only hydrogen spectra, so we will not touch Cl. It is a quadrupolar nucleus. This molecule has a CH3, one type of H, a CH2, another type of H. Remember one very important point, wherever such type of moiety is involved, CH3, CH2, and characteristically we get a quartet for CH2 and a triplet for CH3. I repeat, the identification of ethyl moiety in a molecule, triplet for CH3 and a quartet for CH2, and where the splitting is caused only by hydrogen or by fluorine or by phosphorus 31. The formula given in the previous video reduces to n plus 1 rule, where n is the number of splitting nuclei because the spin is half. So in this case, we have calculated the number of lines. When CH2 absorption is split by CH3, n is 3. When CH3 absorption is split by CH2, n is 2. So on calculation, we get the values quartet for CH2, triplet for CH3. Get another example, 2-bromo, 1-chloropropanone, propane. This molecule clearly shows three types of hydrogens. Here, the CH3 signal is split by CH near Br into a doublet. Likewise, CH2Cl hydrogen signal is split also by CHBr hydrogen, another doublet. The middle hydrogen, CHBr hydrogen, is split by both CH3 into quartet and CH2 into triplet. Multiplication gives 12. So we expect a very complicated spectrum for the middle hydrogen in this case. I repeat, CH3 will be a doublet, CH2 will also be a doublet, but CH signal will be a multiplet. Some more examples. CH3F. If we record proton spectrum, then three hydrogens are identical, equivalent. The signal will be split by single fluorine atom. Applying n plus 1 rule, one fluorine atom split the signal into two. If we record fluorine spectrum, using different set of the instrument, then the signal of fluorine will be split by CH3, three hydrogens, n plus 1 rule gives quartet. Another example, CH2F2. For proton spectrum, signal is split by two fluorines into three, 1 is to 2 is to 1. Likewise, the signal for fluorine spectrum is split into two, 3, 1 is to 2 is to 1 by CH2 hydrogens. For trifluoromethane, the hydrogen spectrum is split by three fluorines into a quartet, and fluorine spectrum is split into a doublet. Coming to the case of phosphine, phosphorus has spin half, so hydrogen spectrum will be split by one phosphorus atom into a doublet. And the hydrogen spectrum will be a doublet, splitting caused by one phosphorus atom. On the other hand, the spectrum of P31 will be split by three hydrogens into a quartet. So one more important point, modern sophisticated instruments have facility for recording the spectra of proton, phosphorus, fluorine, carbon, but different settings of frequency and magnetic field are used. One set of radiating frequency and magnetic field gives only proton spectrum. Then for fluorine or phosphorus or carbon-13, the setting of the instrument has to be changed. The same spectrum does not appear for fluorine and hydrogen. Separate spectra are recorded. Calculation of number of lines and statistical weight factors. Two methods are involved. First, let us understand how it is caused. Suppose some spectrum is split by a single hydrogen. Then what happens? The splitting hydrogen nucleus spin could be either parallel or anti-parallel. So two possibilities are existing. Therefore, we get a doublet. When the splitting hydrogens are two, then three possibilities. Both plus plus, first plus, then minus, first minus, then plus, both minus minus. So there are three orientations possible, but one of the orientations has twice doubled. Therefore, we get the three lines not of equal height, but in the ratio 1 is to 2 is to 1, because the statistical factors are not the same. Here it has been clearly shown when both are plus plus, total spin becomes 1. When both are minus minus, total spin becomes minus 1. When one is plus, one is minus, total spin becomes 0, but two such possibilities exist. So in this case, we get three lines. The intensity ratio 1 is to 2 is to 1. Let us consider splitting of CH2 by CH3 hydrogens. There are three hydrogens which are causing splitting. So how many possibilities of spin orientation are there? Four possibilities, not of equal probability. All three hydrogens spins plus plus plus. Alternatively, 2 plus 1 minus. Three possibilities for this. Or 1 plus 2 minus, again three possibilities. All minus minus minus, only one possibility. For this region, we get a quartet, and intensity of lines or height of lines is nearly 1 is to 3 is to 3 is to 1, not equal. So in this manner, we can solve the problem of both multiplicity and relative intensity of lines. Intensity calculation, there are two methods. The statistical weight or degeneracy of each line of a split signal is calculated on the basis of possible arrangement of spins. One spin has either parallel or anti-parallel arrangement. Hence, 1 is to 1 doublet appears. When splitting is caused by two equivalent hydrogens, three arrangements are possible. When splitting is caused by two non-equivalent nuclei of spin of each, there appear four lines, doublet of doublet, DD, of equal weight, 1 is to 1 is to 1 is to 1. The weight factor is the same as the coefficient in the expansion of binomial equation, that is 1 plus x whole power n, or a plus b whole power n. I have solved it here. When the power is 0, it becomes 1 on a split signal. When the power is 1, we get on expansion 1a, 1b. It means the doublet of equal intensity, 1 is to 1, will be appearing. When the power is 2, then expansion gives 1a square plus 2ab plus 1b square. It means three signals, intensity ratio 1 is to 2 is to 1. When there are three splitting nuclei, expansion of a plus b power 3 gives 1a cube, 3a square b, 3ab square, 1b cube. The coefficients are 1, 3, 3, 1. So we get a quartet. Intensity ratio 1 is to 3 is to 3 is to 1. When there are four such nuclei, causing splitting means two CH2s on either side. Then expansion gives the coefficients are 1, 4, 6, 4, 1. So we get a quintet, 5 lines, intensity ratio 1, 4, 6, 4, 1, and so on and so forth. There is an alternative method, simple method called Pascal's triangle method. Number of splitting nuclei 0, 1, 2, 3, 4, 5, 6 are shown. Weight factors when there is 0 splitting nuclei means no splitting, singlet is observed. When there is 1 splitting nucleus, 1:1 doublet is observed. When there is 2 equivalent nuclei causing splitting, then a triplet 1:2:1. And 3 equivalent nuclei causing splitting, quartet 1, 3, 3, 1. When there are 4 equivalent nuclei causing splitting, 1, 4, 6, 4, 1. When there are 5, 1, 5, 10, 10, 5, 1. When there are 6 splitting nuclei, means 2 methyls on either side, then the splitting coefficients are 1, 6, 15, 20, 15, 6, 1. So in this way, we can calculate how many lines should appear and what should be their relative intensity by having the number of lines in the multiplet and the relative intensity. We derive a lot of information regarding the structure. Actually, chemical shift and multiplicity both are the gist of NMR spectrum analysis. Spin-spin coupling constant parameter. For some system we have shown here in J units. Units are hertz or cycles per second. HH coupling is nearly 276 hertz. HF heteronuclear coupling is nearly 521. Average values are shown here. Geminal CH, matlab nile means most hydrogens on the same carbon, -20 to +6. Splitting between carbon 13 and hydrogen in the range of 120 to 260. Splitting between two hydrogens on adjacent carbons means vicinal 5.5 to 7.5. Splitting between two hydrogens which are cis to each other 7 to 10 dps. For trans situation is a bit higher, 12 to 19 dps. For benzene derivatives, J ortho is a bit visible, 6 to 9 hertz. J meta is very small, 0.5 to 4. J para is smaller still, 0 to 2.5. So J values are very indicative of the structural moieties, their geometrical orientations. Typical spectral data. Ethyl ethanoate. You can carefully see there are 3 types of hydrogens, CH3 near CO, CH2 near O, and CH3. So we get singlet for CH3, quartet for CH2, triplet for CH3, and the chemical shift values follow the order OCH2 greater than CH3CO greater than the remote CH3. Another example is 2,2-dichloropropane. In this case, all the 6 hydrogens are chemically equivalent. So one unsplit peak appears. 1-chloro, 2-iodoethane. We have two kind of hydrogens, CH2Cl and CH2I. So we get two triplets. The case of 2-methyl propene is very interesting. It appears that both hydrogens HA and HB are magnetically non-equivalent, but actually they are equivalent. Why? Because this molecule possesses symmetry, mirror plane symmetry, as well as C2 axis of rotation. So when the molecule possesses symmetry, then the hydrogens cannot be magnetically non-equivalent. They must be equivalent. So in this case, we get one signal for methyls, one signal for CH2 hydrogens, and no splitting is caused. Means the CH2 hydrogens are non, not CH2 hydrogens are equivalent, magnetically equivalent. Splitting is not caused because the separation is more than 3 single bonds. The ethyl hydrogens appear somewhere near 1.76 ppm, and the CH2 hydrogens appear near 4.7 ppm. Some problems, simple problems, and their solutions are shown. 1-chloro 2,2-dimethoxypropane. You can see unsplit signal because hydrogens are not on adjacent carbon atoms. Three signals, not three, two signals, sorry, two signals. One for the CH3, one for CH2. You see carefully the structure. The three methyls are equivalent. Then a molecular formula C8H10, it could be paraxylene. If it is paraxylene, it should show two singlets. If it is ethyl benzene, it should show three signals. Get another example, CH3, CHD, PCl3. In this case, the methyl signal will be split by one hydrogen, not by deuterium. Magnetic moment of deuterium is very small. It causes very little splitting. We can ignore it. So methyl hydrogens will appear as a doublet and CH will appear as a quartet. I repeat, splitting will be caused only by hydrogens, not by deuterium. Deuterium is a magnetic nucleus, no doubt, but its magnetic moment being so small, splitting by it can only be observed at a very, very high resolution. So for simplicity, we can ignore it. Another case, methyl acetate, two singlets. At another case, ClCH2, CH2Br, two singlets. So in this manner, we can analyze the spectrum, we can understand the relation between chemical shift values, very important parameter. Splitting of signals complicates the spectrum but provides very much information about the neighboring situation. So for analyzing NMR spectra, we need a number of parameters, and by practicing simple examples, we can learn how to approach the problem. Some more problems are given below. Molecular formula is C3H8O2. The compound gives two singlets. We have to find the structure. So it is dimethoxymethane. Another problem, formula is C5H12, one peak. So if you work out, there is only one possibility. It is neopentane. The formula is C6H12, one peak. Two possibilities exist. Cyclohexane or tetramethyl ethylene. We have to decide between these two on the basis of chemical shift values. For cyclohexane, it is 1.44. For the other one, it is a bit larger. Another problem, C3H6O2, two singlets. It means one possibility is methyl acetate. But the chemical shift data must be given for full analysis. Another formula, C4H8O2, one peak. If only one peak is appearing, then the molecule must be 1,4-dioxane, no other possibility. C3H6, one peak. If only one peak is appearing for this molecule, it must be cyclopropane. So in this manner, what we need to do, if molecular formula is given okay, then we have to think of the possible structures. And then for each structure, we can correlate the other information given, means number of signals, whether singlet, doublet, triplet, quartet, etc. So by taking into account all these parameters, NMR spectra of the compound helps very much helpful for revealing the structure. This here comes the end. Thank you very much and wish you big success in life. Thank you very much.